Hello everyone, welcome to the lecture on instance segmentation. Let's start by defining the problem. So in the last lecture we saw what the task of semantic segmentation is. Essentially what we want is to label every pixel, including the background, into a semantic class. So we want to label a pixel into sky, grass, road, but also into objects that at the time of doing semantic segmentation we're not really counting. So essentially all the pixels that are coming from different instances of the same class are labeled with the same label in the task of semantic segmentation. You see, for example, here that we're labeling all the pixels belonging to these three cars with the same label, which is the label car. So in semantic segmentation, the objects that can be counted, like cars or people, are treated in the exact same way as the objects that cannot be counted, like sky, grass, or road. Now for the task of instance segmentation, we want to go one step further. Essentially, we don't focus on labeling pixels that are coming from uncountable objects like the sky, grass, or road that we were discussing before, and we focus only on segmenting the pixels that are coming from instances of the same class of objects that we can actually count, for example, cars or people. And the idea here is that we do want to differentiate the pixels that form one car, one instance of a car, and differentiate them from the pixels that form another instance of another car. So essentially, instead of assigning the same label to all the pixels that are forming these three cars, we now will assign different labels to, for example, the yellow car, the first instance, and this blue-green car, which will be a second instance. So not only we want to find the semantic class of the object, but we want to find what kind of instance is that object within that class. Is this one instance? Do the yellow pixels here belong to the same instance as the blue-green pixels there or not? So differentiate between semantic classes and differentiate between instances. So we can go about doing instance segmentation in two ways. The first way is to use the knowledge that we have from object detection and start with a series of proposals. So essentially we would start with, for example, object proposals, and then in a second step we would assign a semantic class to each of these proposals. Now, of course, in the first step we do the actual instance separation with the proposals, and in the second step we do the semantic part and probably also the segmentation part. So this is one way to go. The other way to go is what I call the Scn-Based method, which essentially starts from the semantic segmentation map. So here, for example, I see an example where all of these instances are labeled as person. And so in a second step, what I need to do is I need to separate the instances inside of this semantic label. So let's focus first on the second type of methods. So of course, the great advantage of Scn-based methods is that they start from a semantic map. And we saw in the last lecture already how to do this. And we saw that this was usually done with fully convolutional networks that were able to act on any image size. And this is why Scn-based methods are actually so powerful, because they start from an already pretty good semantic segmentation. So of course, once you get the semantic segmentation, your goal is actually to separate the instances within each of the classes. And there are three methods that I would recommend you to read outside of the lecture to get more in depth on how do they actually perform instance segmentation. And I will talk about the second method just briefly to give the intuition of how to go from edges to instances with multicad. So a lot of the methods that actually want to find instances inside a semantic map, they use the concept of clustering. So you can imagine that you have a set of pixels that actually represent the class person. And within these pixels, what I want to do is I want to cluster the pixels that actually belong to one instance. So in this case, what this method proposes to do is to start from the input image, perform semantic segmentation, which gives you the per pixel semantic class scores, and then try to perform an image partition that would actually separate the images into small sets, like for example, superpixels. So groups of pixels that show certain characteristics, for example, a smooth transition in the color space. And once you have this separation here, now what you want to do is you want to put these superpixels together into instances. So these two branches act in kind of a parallel way. So the left branch performs semantic segmentation. The right branch actually performs separation of the image, and usually this is done using very low-level features, like for example, edge detection. And from this you want to obtain these superpixels, which will then be your units that you will want to put together into instances. So I'm not going to go into more details on these methods because we want to focus this lecture on proposal-based methods. And this is because so far they have shown a much better performance. So what are proposal-based methods? Well, we already know how to obtain bounding boxes, how to do object detection. And this is essentially what proposal-based methods are leveraging. So if you already know how to separate different instances of the same semantic class, so different objects, different cars, for example, with object detection, why not use it as a condition, as your input, essentially, and then trying to find the segmentation mask within this bounding box. So of course, it is much easier if you already have a bounding box and you know that the pixels of your instance can only be found inside this bounding box. It's much easier to find the appropriate segmentation mask than if you start from all your image and you're just looking at the pixels. There are two proposal-based methods that I want to mention, and I also propose you to read follow-up works or previous works just to see how essentially the methods evolves, how one starts with one approach and then evolves this approach to obtain better and better results. So in this case, we will discuss the CCV 2014 paper SDS, and you can read the follow-up work which was presented at CEPR 2015. And after this, we will focus on multitask network cascades, and you can check then the previous work which was done a year before. So let's start with an overview of SDS. So SDS presents a very simple concept in which proposals are used as a starting point, not only for bounding box prediction, but also directly for region or segmentation prediction. So essentially mask prediction. So the idea here is to start from a set of proposals, which you obtain with any algorithm that you like, and then you perform a feature extraction that is good for bounding box prediction and also mask prediction. So of course you have two separate CNNs here, one that predicts the bounding box, the other one that predicts the region. And then the idea is that combining these two sources of information, you can perform region classification and then use other methods for region refinement. So the idea to keep in mind here is that there is a separate head for the box prediction and a separate head for the mask prediction. Multitask network cascades, on the other hand, proposes a slightly more complex approach. So the idea is always to start from this region of interest, these proposals, which you are first going to convert into mask instances and later refine into categorized instances, therefore assigning a class to each of these instances. So in this case, we also start from these proposals and we compute everything by just looking at the region of interest, which is pooled, which is warped, and we can nicely work with it to create our mask instances and our categorized instances. Now, one question that one might ask yourselves is, why should I constrain my method to a fixed set of proposals, which might be incorrect, might contain some imprecisions, or why should I constrain myself to a semantic segmentation map? Ideally, what you would want is to leverage the best of both worlds, to leverage the proposals, which give me a lot of information on instances, and to also leverage the semantic maps, and not start from one and then try to derive the other. So this is essentially how we come to one of the most famous methods for instance segmentation, mask RCNN, which derives from the work of fast and faster RCNN, which we saw in previous lectures. So in mask RCNN, we essentially start from the faster RCNN architecture that we already know. So we have our famous image of the penguin, which is processed by the CNN to perform feature extraction. And from this, we have at the bottom the region proposal network, which proposes these regions of interest, these areas inside the image that are worth looking at. And then faster CNN had the bounding box regression head, which refined these bounding boxes, which actually allowed you to obtain boxes that fit tightly to the object. And also the classification head that tells you whether there's a penguin or there's a cat in the image. This is the basic architecture that mask RCNN starts from. And the main idea is to add a third head. So to add a head which is very much based on fully convolutional networks to perform instance segmentation. So you take kind of the best of both worlds. You take the power of fast RCNN and the proposals and the detection power, and you take the power of fully convolutional networks to perform semantic segmentation. So this is another depiction of what I mean by this combination, this fast RCNN plus the FCN-like mask head. So we have the fast RCNN architecture depicted on the left. We have our regions of interest that are going to be pooled with an operation that is very similar to Roy pooling, but it's now going to be slightly adapted, and we will talk about this. So in this case, we don't have Roy pooling, but we have an operation that is called Roy align. But the idea is, again, to convert any bounding box size to a fixed representation so that then we can predict the class box, and with a series of other convolutions, we can also predict the mask. And the mask loss is essentially going to be a binary cross entropy per pixel for the case semantic classes. So we're going to directly try to predict the semantic class for that particular instance. Now, of course, the idea is that the whole instance problem has already been solved by faster RCNN. Faster RCNN already gives us this separation between objects, and therefore the mask head can focus entirely on finding out the semantic class of this instance. Now, the semantic head, as I said, is a series of convolutions, right? It is a fully convolutional network, FCN. And the idea is that you take your feature representation that still contains some spatial information. And this is the representation before we actually have the classification head and the bounding box regression head of faster RCNN. So we take this representation and we essentially do a series of convolution operations to process it until we have a nice output in which we can represent the semantic classes. So the power of mask RCNN is that most of the features are shared. So most of the computation is shared. So we're really adding only a few operations on top of fast RCNN in order to produce the segmentation results. But let's now look at the two tasks of detection and segmentation. Can we actually use the same operations inside a neural network to perform detection and segmentation? So in the case of detection, we essentially want to do object classification. So once you have a proposal, you want to take that box and you want to perform classification. Is this a cat, is this a dog, or is this not an object at all? So you actually require invariant representations. And in particular, you require translation invariants. So wherever my penguin is inside of the image, I still want to classify it as a penguin. Therefore, I need translation invariant representations to perform detection. Let's look now at the segmentation problem. The segmentation problem is slightly different. So for every translated object, I need a translated mask. And for every scaled object, I need a scaled mask. Therefore, I'm going to require equivariant representations. Also, for semantic segmentation, the small objects are less important because they have less pixels and therefore they count less in the loss function. But for instance segmentation, all objects, no matter the size, are equally important, same as for object detection. So I'm going to need slightly different representations. I'm going to need to make more changes to faster CNN in order to have an equivariant network instead of a network that gives me invariant representations. So what kind of operations are inside faster CNN, and what kind of operations are equivariant and therefore I can keep, and what others are invariant and therefore I need to change in order to create mask RCNN. So let's look at the first type of operation. The first type is the feature extraction, which is performed using a series of convolutional layers. We all know that these operations are equivariant, so no problem there. And the same goes for the segmentation head, right? It's a fully convolutional network, so these operations are also equivariant. But we have one problem in the middle with faster RCNN. So remember that we had the operation of Roy pooling, and we had a series of fully connected layers, and all of these operations essentially give invariance to the representation. So these are not operations that we can keep for mask RCNN. So remember how the region of interest pooling operation was working. So if you remember, we had this proposal that is on top of my penguin. I perform feature extraction with my CNN, and now from my feature map, I'm only interested in looking at the region of my green proposal. So what I do is I put on top of this proposal an H by W grid, and then I perform pooling for each of these regions in order to obtain a map that is H by W by C. So essentially what I do is I bring all proposal representation to a fixed spatial size of H by W with this pooling operation. So what is the exact problem at this pooling operation? Let us look at the example with specific sizes. So let's assume that I have my 400 by 400 image and I have my bounding box, which is 300 by 150. Now once I pass it through a CNN, of course, my feature map has been reduced in spatial size and now has more channels. We will just represent the number of channels as C because we're not interested in how many channels we have, but we're interested in the spatial size, which is now 65 by 65, coming down from 400 by 400. So this of course means that my bounding box has also been scaled down. And for example, the height, which was before 300 pixels, is now 48.75 pixels. So now let's imagine that I take my grid, I take my H by W grid, and I put it on top of my box, which has a height of 48.75 pixels. Now what ends up happening is that I have to choose how many pixels to take into my grid. I cannot take 48.75 pixels and divide it by the number of bins that I need when I put the grid on top. So I need to make a choice, and I, for example, make the choice of 48, right? So this is the first quantization effect that we're going to see. So of course, in the output, we're going to have this quantization effect reflected because now my bounding box is not truly 300 pixels high, but it's much less due to the quantization and due to the fact that instead of taking 48.75, I took 48 as the box height. So of course you can think that this is not really suitable when you want to extract pixel-wise precise masks. If I'm already having a quantization problem only when I predict the bounding box, if I predict pixel-wise precise mask, I'm going to lose a lot of the mask only with this operation. So it is clear that Roy pooling is not suitable for masker CNN. So the idea of masker CNN is then to essentially exchange all the invariant operations with operations that are equivariant. And in this case, they're going to exchange the ROI pooling with an equivariant operation which they call ROI align. So one of the goals of ROI align is to actually erase those quantization effects. So if we look at the example before where we had our 300 pixel box that was converted to a box height of 48.75 in our feature map, before we had to choose, for example, 48 in order to perform ROI pooling. But the idea now is that we're going to be able to choose exactly 48.75 and still perform this region of interest pooling operation, which is now called ROI align. So let's look at this example where we have our feature map here on the left and our bounding box, which is depicted in this salmon color. Now from this bounding box, this ROI, this proposal, we want to get as output from the ROI align operation a fixed dimensional representation, which in our case is a 2 by 2 representation. So essentially, we need to fill these 4 positions. We need to obtain this one value for each of these positions. But of course, for each of these positions, we actually have all of this area to cover and to kind of distill into this only one number. And of course, instead of doing any quantization here, what we say is we want to take into account really the values that can be found in this representation in the exact position where they are meant to be, without any quantization effects. So essentially what we do is we sample each of these units, each of these output regions, into 4, so we sample it 4 times. Now these points are going to be the grid points for the bilinear interpolation. So essentially what I'm going to do is I'm going to take the pixel values that I do have from my feature map, right? My feature map contains values at each of these corners here. So of course there is no value that represents this position here. But what I can do is I can do bilinear interpolation between these 4 corners of my orange box. And bilinear interpolation actually means that, of course, this value is going to be much more influenced by the bottom left corner of this orange box because it is very close to that corner there. But you're still going to take into account the values that can be found on the other corners of my orange box. So through bilinear interpolation, I can essentially create a true value for this blue point, for these grid points. And now what I can do is I can essentially condense this information through, for example, max pooling in order to obtain one output value for the ROI align. So this essentially avoids all the quantization effects and really takes into account the actual value in the actual position of the feature map and not a quantized value, which is not accurate enough for segmentation prediction. And we can see that actually masker CNN works really well. So the qualitative results are really impressive. We get a lot of objects, small and big. They are quite well segmented. Semantic classes are correct. And we can actually use the same network to segment lots of object categories, from person to motorbike to cub to donut. And the nice thing about mask-RCNN is that it's a quite flexible architecture, right? So you can also, for example, extend it to predict body joins. So the idea is that you can actually model a key point location as a one-hot mask and adopt mask-RCNN to predict K masks, which are in the end only one pixel. So every joint is going to be represented as a mask, and you're going to predict K masks for K joints. And each of the masks is going to represent left shoulder, right elbow, and all the other joints in the body. And so essentially, by just slightly changing the meaning of the representation, you can use the same operations and you can take advantage of the Royal line power to actually predict precise body joints in this case. And of course, the full skeleton as is depicted here. So now the question is, can we actually do better, right? So there are works that have been building up on top of mask-RCNN and trying to improve the accuracy of mask-RCNN. So of course, one problem is that the mask quality score is computed as the confidence score for the bounding box. So essentially, if your bounding box doesn't have a high confidence score, then your mask quality is also going to suffer. And remember that the mask loss just evaluates if the pixels have the correct semantic class, not the correct instance. So for example, in this case, where we have 3 persons, if all of the pixels inside the orange bounding box were classified as a person, then it doesn't really matter if this is the purple person or the orange person. You see that there are pixels from both instances falling inside the orange box. This is not really reflected inside the mask loss, whether these 2 instances inside the same box should actually be the same or not. The only thing you're interested in there is that all of these pixels are classified as a person. So of course, this is a problem in this particular case where you have 2 instances or more of the same class, in this case the class person, inside one bounding box. So the idea here is that if you're actually predicting instance segmentations, but the only way the actual instance is evaluated is through the box loss, then you are losing some mask quality in there. So this is why in a subsequent CPR 2019 paper, there were other authors that actually proposed what is called mask scoring RCNN, which was essentially a mask intersection over union head. So the idea here is that you actually want to measure the intersection over union between the predicted mask and the ground truth mask. So you want to have a loss that is really acting on the instance level, on the mask instance level, and not only on the bounding box instance level. Now, typically the mask scoring RCNN gives actually lower confidence scores than mask RCNN because, of course, the masks are not perfect, but this tiny modification actually achieves much better results. So just by having the proper loss, this is something that really changes how your neural network is going to train and what kind of outputs it's going to predict. So of course, mask RCNN derives from fast RCNN, which is a 2-stage detector. And we saw that besides 2-stage detector, we also had 1-stage detectors, which were actually faster. So now the question is, can I also apply this 1-stage, 2-stage concept to masks? So essentially, can I have 1-stage instance segmentation methods? So as I said, in detectors, we had this difference between 1-stage methods like YOLO that had faster but lower performance than faster RCNN versus 2-stage detectors like, for example, faster RCNN and all variants, which are of course slower but have a higher performance. So now we saw as a 2-stage instance segmentation method mask RCNN, which we also hope that is slower but has actually a higher performance than the one-stage counterpart, which is actually YOL-ACT. So even though masks are actually a very meaningful representation, it's not so easy to extend YOLO to predict masks instead of boxes, and this was already found by the creator of YOLO. So it wasn't until 2019 that we got YOL-ACT appearing at a conference. YOL-ACT stands for You Only Look at Coefficients. And the idea there is actually not so straightforward. So to go from boxes to masks, you need to actually design the network carefully. So what they proposed to do was this pipeline, which we will analyze a bit more in detail here today. So as a first step, you actually need a network, a head, that actually generates what they call mask prototypes. So possible segmentations for a particular bounding box. Then you can generate the mask coefficients with another network called the prediction head, which actually evaluates each of the mask prototypes. And finally, you will have a third step in which you will combine the mask prototypes and the mask coefficients to actually generate the final instance segmentation. So let's see the architecture in a bit more detail. We have the backbone, which is actually ResNet 101, and the features are computed at different scales. So we also have this feature pyramid, which is now pretty much present in all object detectors and segmentation, instant segmentation methods. We then have the Protonet, which is responsible for generating K prototype masks. And actually this K has no relationship with the number of semantic classes, but it's rather a hyperparameter. So you generate a fixed number of prototype masks, which you can somehow relate to the anchors that we had in bounding box. The architecture of Protonet is actually a fully convolutional network, which consists in a series of 3x3 convolutions, and then a final 1x1 convolution that simply converts the number of channels into these K predictions that we actually need to have. And in each of these channels at the end, on this feature map of 138 by 138 by K, we will have actually K possible mask prototypes. So this is actually very similar to the mask branch in mask-RCNN, but there is no loss function applied at this stage. So this is actually a very crucial difference. So once this Protonet has generated the mask prototypes, we have another network that predicts a coefficient for every predicted mask and just judges how reliable the mask is. So the mask coefficients are essentially intertwined also with the box predictions. So essentially we have a series of anchor boxes that one can predict, and one can predict the class of the anchor box, a regression to actually fit this anchor box tightly to the object, and then these K coefficients, one per prototype mask and per anchor. So note here that we have W by H and then multiplied by K, which is the number of prototype masks, and multiplied by A, which is the number of anchor boxes. So we have these K coefficients per anchor. And these are actually the ones that define the mask. And note actually how the network is similar to RetinaNet, but a little bit shallower. So essentially now the question is, how do I actually generate the mask from these mask prototypes and these mask coefficients? So essentially what you do is a linear combination between the mask coefficients and the mask prototypes. So you're going to predict a mask as this linear combination and then pass through a nonlinearity. So in this case, P is the H by W by K feature map, the output of Protonet, which is essentially the matrix of prototype masks. C is an N by K matrix of mask coefficients that have survived NMS, also Remember that the coefficients are predicted together with the anchor boxes, so the NMS can be applied on that side. And then sigma is a nonlinearity. So you can see here an example of how you actually construct the final mask by assembling these sort of pieces of masks. So you have here on the top side, first of all, these images are the prototypes, and these are the coefficients, positive coefficient, negative coefficient. And then you have, for example, the mask that has this person with the racket. Here there's only the person. Then we have a negative weight on the prototype that actually represents the racket, which what it essentially gives us is this separation between the two objects. So the separation between the human, the tennis player, and the racket, which is actually another object. Therefore, with this assembly of mask prototypes, we can actually obtain the two instance segmentations separate. One is the tennis player at the top, and the other is the racket at the bottom. And you can see that these are in fact the same prototypes that we use for both detections, and it's just about the coefficients, whether they're positive or negative, that actually define the final mask. And thanks to these coefficients, we can separate the person from the racket. Now, as a bounding box for YOLA, we're going to have a simple cross-entropy between the assembled mask and the ground truth, in addition to the standard losses, which are the regression for the bounding box and the classification for the actual semantic class. And the results are actually pretty good, so we can see that we can segment a lot of semantic classes, a lot of instances with quite a large degree of occlusion. So see, for example, these two persons being separated correctly. And the method is, of course, fast because it's a one-stage segmentation method. Now, for large objects, the quality of the masks is even better than those of two-stage detectors, but of course the quality is a little bit reduced for small objects. So for small objects, the quality is not as good as for masked CNN. Now, of course, the main selling point, right, is the FPS, so the frames per second that YOLA is able to process. And of course, compared to masked CNN, we can see that YOLA is actually much faster. It's a little bit less accurate, but of course, it depends for what kind of application you want to use it. If you want to use if you want to have some segmentation output in real time, then you have to use YOLA. This is the only method up to this point, up to 2019, that was actually reaching these real-time capabilities. So of course, if you need the real-time, then you might be able to sustain this little bit of a drop in precision. So then, of course, there are improvements on top of YOLA, right? So the authors have been actually active in developing YOLA++, and you can read the paper there. There is actually a specially designed version of non-maximum suppression in order to make the procedure even faster, and an auxiliary segmentation, semantic segmentation loss function, which is performed on the final features of the SPN. So trying to bring a little bit this idea of the FCN concept that actually looked at all the image in order to predict semantic segmentation results. Okay, so we have seen semantic segmentation in the previous lecture. We have seen instance segmentation in this lecture. And now the idea is, why not combining both concepts? So remember that semantic segmentation labels each of the pixels in the image with a unique semantic label. And this means that all cars are going to have the same label car. And it's only through instance segmentation that we can separate the different cars within this label. But the problem with instance segmentation is that it does not give us any label for the things that are not countable, for example, the grass, the sky, or the road. So the task that panoptic segmentation is trying to resolve is actually the task of combining semantic segmentation and instance segmentation. Therefore, each pixel needs to receive a label, a semantic label, and at the same time, if possible, if the object is countable, you need to receive essentially an instance label. So for semantic segmentation, we have the FCN-like methods. For instance segmentation, we have MaskRCNN and YOLACT and other derived methods. And for panoptic segmentation, we have what is called the UPSNet. Of course, now we have many more methods that are trying to solve the panoptic segmentation task, but this is one of the first methods that actually tackle the task of panoptic segmentation. So in panoptic segmentation, we have to predict both the labels for uncountable objects, which we call stuff in computer vision, so things like sky, road, grass, etc., for which you cannot really differentiate between different instances. And the labels are usually obtained with networks similar to the fully convolutional networks that we have seen for the semantic segmentation tasks. And on the other hand, one also has to label all the objects which belong to the countable classes. So these countable objects, which are called things in computer vision, cars, pedestrian, for which we actually also have to differentiate between pixels coming from different instances of the same class. So differentiate between car 1, car 2, and car 3. Now, of course, if we just tackle the task with an FCN and a MaskRCNN separately, some pixels might get classified as stuff from the FCN network, and at the same time, they might be classified as instances of some class from MaskRCNN. So if we just kind of put together FCN and MaskRCNN for both tasks, we might have conflicting results. So the solution that they propose in this CPR19 paper is very simple: a parametric-free panoptic head, which actually combines the information from the SCN and the MaskRCNN. So essentially what we want to do is we want to create this network that combines both the stuff classification as well as the things classification. And the network architecture looks like this. So we have a set of shared features, right? We don't want to have two completely separate networks, but we actually have this set of shared features with also feature pyramids. Then we have the semantic head on top, which is the one that gives us the semantic segmentation, and the instance head at the bottom, which is essentially MaskRCNN inspired. And in the end, we're going to have this panoptic head, which actually puts the information together and puts the semantic logics and the instance logics together to create what they call the panoptic logics. So let's take another look at this semantic head because it has some interesting design choices. So in particular, the semantic head is a fully convolutional network that outputs the semantic logics or the semantic segmentation map. And the new thing that they use in this architecture are deformable convolutions. So before introducing the concept, we're going to recall the dilated convolutions because these two types of convolutions are actually very similar. So if you remember, a normal convolution, which would be a convolution with dilation parameter 1, would be as the operation depicted here in this image A. So in this case, we have a 3x3 convolutional filter, dilation 1, which means a normal convolution, hence the receptive field is 3x3. With the same number of parameters, but now with a dilation of 2, what we can get is essentially a receptive field of 7x7. And how the dilated convolution actually achieves this is by essentially spreading these weights and not applying them to neighboring pixels, but applying them to pixels separated by 2. Same as if the dilation parameter is 4, then each element produced by it has a receptive field of 15 by 15, but we still have these 9 parameters to learn. So we increase the receptive field without increasing the number of parameters. Now, a deformable convolution is a very similar concept, but now we're not going to have this kind of stacked dilation, right? In which you just spread the weights, but always in the same way. So what the deformable convolution actually proposes to do is kind of a generalization of dilated convolutions. And in this case, what you want to do is you want to also learn the offset. So essentially, I have here my weights of my 3x3 kernel depicted in green, and now I'm going to learn essentially where to send them, where to get that information to be multiplied by the weight. So of course, dilated convolutions are a special case of deformable convolutions. So in this case, what we need to do is to get our input feature map with a conv layer. We actually learn what is called the offset field, which actually tells us where to send these weights, where to multiply these weights, or by which pixel to multiply these weights in order to create one pixel of the output feature map. And you have here the formulation for regular convolution and deformable convolution in case you want to take a look. So of course, with respect to standard convolutions, deformable convolutions are much more flexible. So you can see here a couple of convolutional layers that are acting on this image and how they create one pixel in the output space at the top. And of course, the deformable convolution will pick the values at different locations in order to compute the actual convolution operation. And these locations will be conditioned on the input image. Therefore, you can imagine that if you actually have an object with a lot of thin structures, you're going to really place your weights in precise location in order to get the most useful information and not just spread the values like in normable convolutions. So this is actually a very interesting operation for segmentation outputs, for when you actually need to have these pixel-wise accurate outputs. So let's go now into the panoptic head. So what is this panoptic head that actually puts together the mask output and the semantic information output? So we have at the top the mask, what they call logits, from the instance head, right? This comes from a masker CNN type of head that tells you where these instances are located and what is the extent of them. The object logics come from the semantic head and tell you what is the probability that this pixel belongs to the class car, the class person, etc., etc. And then you have the staff logics, which is exactly the same, but for the classes which are not countable, like sky, for example, or road. Now, for the staff classes, one needs to do nothing, right? There are no instances there, so one needs to do really nothing. So the staff logics can be evaluated directly. But the objects actually need to be masked by their instance, right? Look at this example where we have this instance of, I think this is a car, and actually all of the extent of the image depicts more things than just this car. But in the end, since we're going to have this mask logic, this instance logic that actually is going to evaluate only this part of the semantic head, right? The rest doesn't really apply because we know that the object is bounded by this bounding box. Therefore, we're only interested in having a good prediction inside this instance box that is coming from the instance head. Therefore, what we're going to do is we're going to perform this operation where we essentially cut what we're interested in, what is actually inside the box that we're interested in. We cut the semantic map with the instance map, and then this is what we're going to use for our instance logics, which are depicted here in green. And the rest of the image, the rest that doesn't fit into an instance, is going to end up in this last channel here, which is actually the channel unknown. And so we're going to perform a softmax over the panoptic logics. And the key here is that if the maximum value falls into the first stuff channels, then it belongs to one of the stuff classes, right? Otherwise, the index of the maximum value tells us the instance ID that the pixel belongs to. And like this, there are no conflicts, right? Because we take the maximum over all the channels, over the instance, over the unknown, and over the stuff. So we have to make a decision between these three. And the last thing that we need to know is actually how to use this unknown class, this last class, which doesn't belong to instances or to stuff. And this is something that I would actually recommend you to read how it exactly works and what are the details on how to use this unknown class in the CEPR 2019 paper. Excellent, so we can now move to the metrics, right? We know how to measure semantic segmentation, we know how to measure object detection, but how do we measure panoptic segmentation quality? Now, the panoptic quality measure contains two parts. The first part, the first term, measures the segmentation quality, meaning how close the predicted segments are to the ground truth segments. And you can see that this is measured with the IOU, the intersection over union of the two true positive masks. So essentially not taking into account bad predictions. So this is just one part of the panoptic quality measure, the part of the segmentation quality. And now we go towards measuring the actual recognition quality. So the same as for detection, we actually want to know if we are missing any instances, which would lead to false negatives, or we are predicting more instances, which would lead to false positives. So we have in this case an example of this ground truth where we have 3 persons, 3 instances, we have a dog, and in our prediction, the sky and the grass are predicted more or less correctly, but there is 1 person missing and the dog is actually misclassified as a person. So in this case, we would have several true positives, right? We would have this light brown person matched, we would have the orange person matched, but this dark brown person is actually not found in your prediction, therefore it is a false negative. And at the same time, we have a false positive from this person, which is actually in the wrong class. So the prediction is the wrong class. So all this match, false positives, true positive computation needs to be done in a similar way as we did for detection. So essentially there needs to be a way to match ground truth and predictions. And in this case, we actually have to do segment matching. So the segment is actually matched if the intersection over union is above 0.5, and as with detections, no pixel can actually belong to 2 predicted segments. So in this case, where we have 1 cat, but we actually have 2 predictions, we compute the intersection over union of the 2 predictions, and we find that the blue prediction has intersection over union of 0.6, therefore is considered as true positive, but the top part of the cat is considered as a false positive because the intersection over union is 0.4. And of course, no 2 segments can actually belong to the same ground truth. Now, qualitatively, results for panoptic segmentation actually look pretty good, so it's quite nice what computer vision can do nowadays. And we can predict stuff classes without the instance IDs, as well as things classes with the correct semantic label, and also by separating the different instances. So for example, here we have the separation of the different classes into different instances. Okay, so finally I will present a third way of doing instance segmentation. And this is a way that I particularly like. And it is inspired to what we used to do a little bit before CNNs came in. So all the RCNN methods, all the methods in the RCNN family, or even deformable part models, use a sliding window approach for detection. So essentially the basic idea, as we have seen, is to densely enumerate box proposals and then classify them. So this is a successful paradigm. We have seen it's well engineered, it achieves SOTA results, and most of the state-of-the-art methods are still based on this paradigm. Nonetheless, before DPM, before RCNN, we used to do detection as voting. Or let's say one of the paradigms that existed for detection was the one for voting. And this was way before we had actually convolutional neural networks. So what do I mean by half voting? So in this case, we can see the very simple example in which we want to detect analytical shapes, for example, lines, as peaks in a dual parametric space. So essentially what we would have is each pixel would cast a vote in this dual space. And then we would detect the peaks in the dual space and kind of back project them to the image space to detect, for example, a line. So let me put it into a visual example. So we want to do line detection. And all we have in order to detect a line are different points that are placed on top of a line. So essentially what we want to do is to fit a line through these points. Now what we can do is that each point in the image space, for example in this case x0, y0, actually casts a vote into the half parameter space. And this vote actually takes the form of a line that crosses that point. So it is important to note that this line, which is parameterized by M and B, is always going to cross the point x0, y0. So essentially this represents all the lines that are going to cross that point. Now if we take another point, x1, y1, we're going to cast another vote. We're going to cast another line in the half parameter space. And so for all the points of this line that we're trying to find out, we're going to cast votes in the parameter space. We're going to cast all of these lines in this parameter space. And then what we're going to do is we're going to go to the parameter space, to the half parameter space, and we're going to read out the maxima from this parameter space. And in this case, the maxima is going to be this point here where all the lines are going to cross. And this point here where all the lines cross is a point represented by a value of M and a value of B that represent the line that actually best fits all of these points that have casted votes. So let's see how can we actually use this to actually perform object detection, not only line detection, but object detection in the form of voting. So the idea is that objects are going to be detected as consistent configuration of observed parts. So in this case, we have a car, and we know that a car has two wheels. And we know that these two wheels are always roughly in the same position with respect, for example, to the center of the car. So the rough idea would be to use the wheel patch, and whenever this wheel patch is detected, I'm going to cast a vote for the center of the car. And I know that the center of the car is always going to have the same relationship with respect to the wheel, more or less. Therefore, I'm going to cast votes from the wheels of the car, the window of the car, the back of the car, the front of the car. They're all going to cast votes to the center of the car. And by detecting these peaks, I'm going to be able to know if there was indeed a car there or not. So let's look at this in more detail. How can we actually train a method to perform this kind of voting? So what I'm going to do is I'm going to first extract some features from the image. So again, this is before CNN. So what we used to use in that period was point detection methods, so interest key point detection methods, for example, SIFT or SURF. And this basically extracted interesting points from the image, salient points from the image. Now from this point, what we did is we placed a patch centered around this interest point, and this patch had to cast a vote for the center of the object. So of course, we took the interest points that were on top of the object, and these were casting a vote for the center of the object, which we had as ground truth. So this was our training procedure, right? Each patch had to learn how to vote for a center point. And at test time, what we would do is we would get the original image, cast these, compute these interest points, find the similarity between the interest point and the codebook entries. So essentially find the most similar patches from our training set and then use the votes from that training set in order to vote for the center of the car. Now this is an interesting example for the car here, right? Because the front wheel and the back wheel have very, very similar appearance. So it is very likely that they're both going to vote, or they're going to vote with the same likelihood for the center of the car, but also for, let's say, the symmetrical position. So in this case, this patch would vote for the center, but also for this position here, which would be the center if this was the back wheel and not the front wheel. And the same happens for the back wheel, which votes for the real center, but also for this point here in the back. Now, the key idea here is that we're going to cast a lot of votes, right? So the windows are going to vote, the front of the car is going to vote, the door is going to vote, and you're going to have votes all over the place, but there is going to be a concentration of votes in the center of the actual object. So in this half parametric space, we can find this peak of votes, right, where the votes really concentrate. Now, once we have done this, then we can do segmentation like this, because we can go back to the image space and we can say, let's look at all the patches that voted for this position here. Now we gather all of these patches, we perform some further post-processing, and now we have a rough segmentation of the object. So this was the method back in the past, no CNNs here. So now we come back to 2020. And we're going to present a paper called Pixel Consensus Voted for Panoptic Segmentation, which was published actually at CEPR 2020. So really recent research happening that merges this concept of voting with the modern CNN and the power of CNN feature extraction. So the overview of this method is we're going to use, of course, our FPN, our backbone to extract features. We are going to have a semantic segmentation branch at the top, so the same that we have been seeing so far. And the interesting part is this part here. So it's this second branch, and it's the instance voting branch. And it actually predicts for every pixel whether the pixel is part of an instance mask, and if so, the relative location of the instance mask centroid. So the same idea as the paper that actually used SIFT to extract meaningful patches. Of course, this is a much more powerful representation because the authors, what they proposed to do was to put this instance voting branch or to code it into operations that you can fully backpropagate through. And therefore, you can train this whole thing end to end. So in a nutshell, how does this method work? Well, first of all, we need to make a decision for each pixel. And what we're going to do is we're going to discretize the regions around each pixel, right? The pixel has a neighborhood. We're interested in looking at the neighborhood in order to make a decision about the centroid, right? So each pixel has to vote for the centroid of the object that it belongs to. So it needs to have an idea of what is going on around it. Now, every pixel is going to vote for its centroid. If it belongs to the category stuff, so essentially no instance in road or sky or grass, then you're going to vote essentially for an extra class which is no centroid. But the main idea is that every pixel is going to vote for a centroid if the centroid is located in this area here. If the centroid is not located in this area here, this is ignored for training. Now, in a third step, we're going to have this vote aggregation, right? Same as we saw in the half space. This vote aggregation at each pixel. And this is basically casted into this accumulator space, right? And this casting is very nicely formulated as a dilated transpose convolution. On a fourth step, we're going to detect these objects as these peaks. In this case, we have these three objects, these three peaks. And finally, we're going to do, again, a back projection of the peaks. So same as we presented for the method before, you look at who voted for that center, you go back to the image space, and you can obtain the mask, which are all the pixels that voted for that center. And the category information, the semantic information, is provided by the parallel semantic segmentation head. Okay, so now the interesting thing is how do we implement this into a neural network, right? So what the authors propose to do is to have what they call a voting lookup table. So first of all, we need to discretize the region around the pixel, right? I am a pixel, I need to cast a vote for my centroid, and I need to know where to cast this vote. So the first thing that I'm going to do is I'm going to place this voting filter centered around the pixel that has to cast a vote. And what this voting filter does is it converts these n by n cells, right, this square center on this pixel, into 17 indices. So essentially, I can cast a vote for 17 positions. Note that there's, of course, much more resolution closer to the pixel and much less resolution as we go further away from the object. Now, in this case, if I am this instance mask and I'm this pixel in the instance mask, my center is the red square. So I basically need to cast the vote for the center, which is going to be on position 16. So me, blue pixel, I'm going to cast a vote, which is actually the value 16. And thanks to the voting filter, I know exactly what this value means in the image space. Now at inference, the instance voting branch actually provides a tensor. And this tensor has size h by w, so image size, and the number of channels is k plus 1. So essentially k positions, remember we had 17 indices here, so 17 positions that I can vote for, plus 1, which is basically for the class, for all the classes that are not countable, so the sky, the grass, or the road. And now the idea is that I want to accumulate the votes in my accumulator space. And how do I actually want to do that? Well, remember again our example of the blue pixel. We get a vote for index 16 with very high probability, right? Probability is 0.9. And this comes from a softmax output with these 17 classifications plus 1. 17 classes, plus 1, where each class is one of these positions in the voting filter. Now, what I need to do is I basically need to transfer this 0.9 value to the cell number 16. So I'm going to do this with a dilated transpose convolution, right? I'm going to place the value in there. And then the other operation I need to do in this particular case is to evenly distribute this value among the pixels. And for this, I'm going to do average pooling. So both of these operations are very familiar for deep learning people, for convolutional neural networks. We know transpose convolution. In this case, it's a fixed dilated convolution, and we know pooling. In this case, it's average pooling. So we can actually map all of these voting operations into essentially convolutional neural network operations. Now, these transpose convolutions, they need to take this single value in the input. And by multiplying it with the kernel, they will distribute this value in the output map. Now, this kernel is actually going to define the amount of the input value that is being distributed. And of course, when we talk about transpose convolution, in general, we talk about learned transpose convolution. However, for this particular purpose of vote aggregation, we actually fix the kernel parameters. And these kernel parameters are this one hot encoding across each channel that marks the target location. So of course, we know exactly where to place this vote. So this is going to be a fixed operation. We're not going to have learnable parameters in there. Now, this is a more detailed example on the voting, on the implementation, and you're welcome to take a look at home. Now, for object detection, what happens then? This is an example where we have these several objects, motorbikes, person. We cast these votes, and now we detect these peaks in the heat map. And these peaks essentially determine the consensus between different pixels in the image, in the instance, that all have voted for the same center. So by simply thresholding and doing some connected component analysis, we can detect the center for all of these objects. Now we need to do the back projection. Now we need to localize the mask of these objects. So for every peak, we need to determine which pixels voted for this center, and therefore favor this region to be the center above all other possibilities. And you see actually that by doing this back projection, we get fairly good results, right? I mean, look at this instance here. By just looking at the pixels that voted for the center, we already have quite a good segmentation of this person. So in order to determine which pixel could have voted for a specific object center, the authors propose to use what they call a query filter, which is essentially a spatial inversion of the voting filter. So see how it's horizontally and vertically flipped? So now the question is, if when I did the voting, I voted for pixel 8, position 8, to be my center, now during back propagation, I look at this pixel and I say, well, the bottom left pixel, right, where the 8 is, should have actually voted for 8 if I'm the instant center, right? This is exactly the opposite operation. And this essentially, by applying this query filter, is how you can do this vote aggregation, this back propagation, where you actually find out which pixels voted for you as a center. And the qualitative results of this voting scheme are also really good. So you can see here, for example, this crazy image with all the teddy bears that are correctly classified, and also the instances obtained are actually really, really impressive. So you might actually wonder, why do we need to go through all the trouble of doing semantic segmentation, instance segmentation, and in the end, panoptic segmentation, right? So the idea is that we want to use a camera in computer vision to understand the scene around us. And the ultimate scene interpretation is to know exactly what every pixel represents. So we want to find individual objects, we want to find surfaces, and for example, for robots, surfaces are really important, right? We need to actually allow robots to understand what are drivable surfaces, for example, a road, and what are non-drivable surfaces. We need to allow the robot to understand the type of objects, the type of obstacles that it can find. And also, finally, and this is not done through panoptic segmentation, but more through tracking and through trajectory prediction, as we will see, we also need to allow robots to understand or to predict the intent of the agents in the vicinity. For example, whether a person is going to cross the path of the robot or not. So understanding the scene around us through panoptic segmentation is one of the pillars actually of mobile robot vision. Thank you very much for following this lecture on instance segmentation. Stay tuned for the next lecture.